Absolutely fantastic. We've got local visitors, we've got national visitors who come from far, some from North of Humber, James. So good to see you. And a couple of international visitors who flew in from Scotland, George and Crystal. So everybody's welcome. So thank you very much. This is the third day of a 3-day conference that Elizabeth and the team have been running here, and it's a celebration of something old and something new. So we've been celebrating something old, which is the end of our Internet Robotics grant, which is £6.8 million research funding, which helped us build these amazing facilities. But importantly, most importantly, building amazing single people to take forward robotics discipline in the market. That robotics is also critically linked with our reports for training. Well, we've had 50 PhD students training in robotics, run by Mark, somewhere over there, and then yesterday we had their quarterly review, and the first time, I think the only time we had the full 50 students actually here. So 50 amazing people that have done careers in agriculture and in robotics, working in Cambridge and University of Cambridge. So absolutely phenomenal. So those reports and CDT is ongoing. Link Agri Robotics goes out at the end of March. And that's one of the size of the programs that we've been running. And then we're celebrating something new. So some big new intentions from a UK Rice facility. That's a new centre of doctoral training called SUSTAIN, which is 60 PhD students, being run by Simon Parsons, Elizabeth and Louise Manning from Leah, and George and Christoph from Strathclyde, University of Strathclyde, University of Aberdeen, and we've had a really nice team. So our collaborative links are expanding, the depths of work is expanding, and our ability to train people is expanding. So think of it, just those two programs, that's 110 PhD students working in AI and agri-robotics, biggest cohort in the world of PhD capabilities. And all practice. That's something new. The other thing we're celebrating something new is our new LeanCamp program. We've got amazing representation from the local enterprise partnership. Over there, and that's a joint program funded by EPSRC, which is £5 million funding, and that's research translation activities. That's the University of Cambridge. It's taken forward a series program. We can now fund any British university who've got a great idea, they want to translate that idea. So that could be a robot system, an AI system, digital system, novel system. So a university can apply for that funding. That translation has to happen in our area, the LeanCamp area. So it's a place-based impact. It's the first time EPS has secured direct funding, and we have all the first opportunities. So with that program will start, and we're looking to some research. But importantly, you spin out new licenses and try and help some of that technology stick and have an impact in our region. That's the whole idea of thinking. So something old, something new. It's been a celebration of 3 days. Over the last 3 days, really the last 5 years' work, I think. So it's been wonderful. And this is the main final meeting of that. So today what we've got is a breakfast briefing opportunity with Elizabeth, who's director of research at NIAT. It's going to give an overview of AI in agriculture. I often give overviews of AI in agriculture, and then Elizabeth tries to keep me straight and narrow and correct. So we're going to hear it from the real globally leading expert in AI for agriculture. That's the start. And then we're also going to hear from Craig talking about what's going on Camden BRI. So Craig's research lead at Camden BRI, which is new technology, I guess, for the wine industry. And we're going to hear two presentations from Elizabeth and Craig. Now, what Craig doesn't know is at the end of that, there's a fireside chat between Craig and Elizabeth. And we've not really told Craig too much. I think we'll give the PhD guy, whenever that was, but I think looking for that. So without further ado, I'm going to hand over to Elizabeth. We're going to try to keep us on time. We're going to close it and we're going to try and move it on. We'll take questions where I think we can squeeze them in, or we'll get questions. So, Elizabeth.
Thank you, Simon. Okay. Good morning, everyone. So, as Simon said, I'm Elizabeth Sklar. I'm a professor in agri-robotics and the research director here. My background is in AI and robotics, and I started studying robotics a long time ago. I started studying AI a long time ago. And one of the things that has been sort of increasingly irritating me over time, especially recently, is the narrowness of people's understanding of what AI is. And so what I wanted to do today was give a broad overview of AI as the whole field, and not just the narrow piece that shows up in the media, something like ChatGPT. So bear with me, I've got some pretty dense slides. I'm going to try to go through things quickly. In fact, I'm going to set the timer on my phone so that I don't run over too much. Craig has time to do his slides. So let's get started. The structure of my talk looks like this. As the title said, the context is about sustainable agriculture. So I'm going to give some examples about how AI works, how it's useful in sustainable agriculture applications. And I'm going to talk in general, what is AI? And then most of the bulk of what I'm going to talk about is a bit about how AI works. And then what AI is good for, leading into what Craig is gonna talk about. So let's get started. The context is something I'm assuming with this audience is mostly familiar. Feels like the audio is going in and out. Is that all right? So the agri-food sector, of course, has many challenges being faced. I've brought up a couple of the UN Sustainable Development Goals, looking to fight climate change, looking to address food security, and of course, we live today in a complex socio-political landscape. And so there's a number of these different kinds of challenges that we're looking to address. And these are some things that AI and robotics can help us with. So promoting carbon sequestration, offsetting greenhouse gas emissions, eliminating practices that harm the environment, making better use of existing farmland and existing labor, and a number of different things that AI can help us with. And so that's kind of the context, the motivation for looking at ways in which AI can help address these kinds of issues. So I'm going to cover a few different types of things, and you'll see on this slide the topics that are listed in purple are things that are going to come up when I give you a general overview of what AI is. So I'm not going to define them here. So perception, knowledge, representation, machine learning, reasoning. I'm not going to define them yet. So it's a little bit of a teaser here. The kinds of things that AI can help with are monitoring environmental parameters. So if we want to be able to look at greenhouse gas emissions and carbon sequestration, we need to be able to monitor and model, what those things are in the environment. We want to be able to adapt. If we're building a model and things change, we want to be able to adapt that model so that it captures what's happening, the changes in the world. And we want to be able to use those models to solve problems. So like making better use of land and available labor. So those are the kinds of things that AI can help us with. And let's look at what different things are, what elements of AI can help us do those things. So here's the early history. For any of you who studied AI, you probably saw some of these guys in textbooks. You've probably heard of Alan Turing before, who came up in 1950 with the paper that is not cited as often as I think it should be, which was called Can Machines Think? And it was really sort of a philosophical paper thinking about, what's the idea of a computer, and could you potentially have some kind of computer system that was intelligent? How would you define intelligence? And so he defined something called the imitation game in his paper, which is known now as the Turing test. If you saw the film, The Imitation Game, then you would have seen this. And basically the general idea is that you have two entities, a human and a machine, and they're both being asked questions. And the idea is that is the person who's asking the questions able to tell whether the answer is provided by a human or a machine. And if you can't tell the difference, then this machine has passed this Turing test, okay, or the imitation game. So it's a famous test that's been talked about, since the paper came out. The other key date in the sort of history of AI was in 1956. There was a summer institute that was held at Dartmouth College, which is a university in the U.S. in New Hampshire, and some guys who became quite famous sort of through that were involved in organizing and participating in that. So you might have heard of names if you've studied computer science or any AI. You might have heard of John Harvey or Shannon, who did a lot of work in information theory. And one of the things that the whole Dartmouth sort of summer program was focusing on was looking at this premise, which I've put in the bottom of the slide here, which says every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it, okay? Now, I think it's kind of amazing that these guys thought about this in 1956. When you think about what kind of computing you have available, in a device like this, all right? In those days, you had a whole room like this big with, temperature control and climate control and big machines with reel-to-reel tapes in order to do the kind of computation now we have in our pocket. So it's kind of amazing that they were thinking about what are the kinds of things that computers could do, even when the facilities and hardware for doing that was not nearly as advanced as it is today. So that's kind of where things started with AI, and I'm not going to go too long into the whole history of AI, but one of the things I started thinking about was looking at, when we teach AI, I've taught AI for a long time in a number of different contexts, and I wanted to look at sort of what's the evolution of how we teach AI. And one of the textbooks that is used quite widely is written by two guys called Stuart Russell and Peter Norvig. So how many people here studied from a Russell and Norvig book? If you did. So many of the people here who are coming from that background used the Russell and Norvig book. Actually, I'm so old that the first Russell and Norvig book wasn't published yet when I first studied AI, and I used a book by Elaine Rich when I studied as an undergraduate, which is just called AI, and that's the one on the top. But I want you to notice the themes here. So the themes around problem solving, around knowledge representation, around uncertainty, learning, and communicating, perceiving, and acting. And I'll talk a little bit about examples of what those things are. But for those of you who have done some studying of AI, it's interesting, I think, to see that the general topics haven't changed that much. But we're really focused right now on this little box here, machine learning. And in fact, this deep learning, which I'll give you a little bit of an idea of what it is. And deep learning for NLP, those are the things that people are thinking of when you look at ChatGPT. Those are the kinds of things that people think of as AI. But that's just a small piece of what all AI is. So that's what I'm trying to get across here. So let's move on. One of the other things I wanted to say, when I put that first slide together, I was like, well, this is a very striking demographic of the sort of fathers of AI. Well, let's look at where we are now. And not only have the topics moved on, but so does the population. And I put up some of the pictures of our colleagues here who may be sitting in the room, just to give you an idea that it has become a bit more diverse, not only in topics, but in including the people who are working in AI. And I'm going to bring up some of these topics as we look at some of the examples going forward. So what is AI and what is not AI, right? So AI is something that can make statistical predictions based on training data, and I'm going to explain what that is. AI can support decision-making for people and also for robots or software agents by modeling situations, by modeling behaviors and relationships between situations and behaviors. AI can improve its models over time. AI does not have common sense. AI is not perfect. Okay, so some of these things are things to keep in mind as you read about and see different kinds of AI applications coming out in the world. AI is only as good as its structure, the data that feeds it, and the method that trains it. And I pulled out this example, right? So there's a little picture of DNA, so that's a structure, biological structure for living things. We're going to look at structures for things that underpin AI. So that's you've got that structure, and then you feed that structure. It's like people are fed with food, you are what you eat. The data that feeds the AI is what creates the kind of intelligence that comes out of the AI, and that is also being influenced by how it's trained. So not only the inherent structure and what's feeding it, but the nurture of how you do that training. And I think that it's really, really important to understand that you could have a beautiful structure and you feed that structure with terrible data, the outcome is going to be terrible. And so it's really important. One of the things that we struggle with looking at AI in the agriculture domain is getting enough data, getting good data to be able to build models that do the things that we want to do. Okay, so let's look at, now we look at what AI is. Let's delve into some of these areas of AI. And I pulled these from the review textbooks. Just have 5 components that we're going to look at. And I'm going to start with intelligent agents, and we'll move on down. Okay, so what's an intelligent agent? It's a way of looking at how a computing system can be intelligent and how it can interact with the world. So an intelligent agent is a sort of canonical image, and I like to use an illustration of a robot because it's something that I think is a bit more graspable than what a software agent is, which is a bit can feel a bit vague. So an intelligent autonomous agent is situated in an environment. So think about a robot that has a physical place that it's designed to work in, whether it's a car factory or a food factory or an airport, it's designed to work in a particular environment. It is designed to perform or achieve a certain set of goals. Now, those goals could be goals just for that individual agent. They could also be what are called group goals. So maybe the agent is doing something on behalf of people, so it has to think about sharing the goals between the robot and the person, or maybe there are multiple robots that are sharing goals. So to me, some of the more interesting things are looking at these multi-agent, multi-human robot environments, and how do you take, everybody in this room probably has individual goals. We're thinking about how you got here, where you're going to go next, what you have to achieve before 5 o'clock today, right? You might have those individual goals, but we might also have some group goals in terms of, making sure that everybody in here is safe, that we all have the breakfast we wanted, things like that. So what are the goals that are used to design the behavior of the robot or the agent? So a robot is an agent that exists in the physical world, but there are also agents, or sometimes called bots, that exist in the virtual world. So you might see them in games, you might see them showing up on delivering emails or other kinds of things that are some kind of automated process that its situation is a virtual world, but its actions will be performed within that environment. So the agents or the robots perceive their environment. Again, if you think about it as a robot, the perceptions are driven by sensors, which are things like cameras, which read information from the environment and then are fed into the brain of the agent to make decisions and help figure out how to do its goals, how to achieve its goals. And usually achieving the goals involves performing some kind of action. Now, it might be a physical action like harvesting strawberries or sending an email, or it might be collaboration action, like saying something and trying to reach agreement with one of the other entities that the agent or the robot is interacting with. Okay, so this is the context for AI. We want to be able to come up with something that takes this input, produces some sensible output. And remember, I said that AI doesn't have common sense. So when I say sensible output, that has to be programmed into the agent to understand what is sensible and what is not sensible. Early AI looked at game playing as a sort of canonical example of problem solving. Why was game playing used? Well, game playing is a very neat environment for studying AI because the environments are structured. They involve a fixed and a known set of rules of behavior, right? So we call it legal moves. So if you play checkers, or you play tic-tac-toe, and you might have another name for it, or chess, or Go, or backgammon. These are some of the games that have been studied with AI, going from the simplest to the most complex. So there's clear rules that you know when you're playing the game, when you learn how to play the game. And there are clear definitions for scoring. So you know whether a particular result of a game, who has won that game. You may not know during the game whether an individual move is going to contribute to winning or losing. You may have to wait until the end of the game to find out, was that sequence of moves the right sequence of moves? And I'm going to talk about that in the context of something called reinforcement learning. But one of the things I want you to take away from this slide is this structure here, this diagram here, which is called a tree. And in computer science, trees are drawn upside down, so the root of the tree is at the top. And this is just an example of what's enumerating the set of legal moves for tic-tac-toe, which, as I said, it's the simplest game here. When you start playing tic-tac-toe, you have an empty board, and there are two players, X and O. I'm going to assume everybody here knows enough about tic-tac-toe that you can follow me. So, and what you'll see is that you start with this empty board here where nobody has gone, and then the X player goes first. There's 9 positions, and so the X player could go in any of 9 spots, and those are enumerated in this tree. Okay, so the X player goes, say, in this spot, the upper left corner, which if you studied tic-tac-toe, you know that actually the best place to go is the middle. But anyways, this example has expanded the tree from just going in that upper left corner. And then if you go in that upper left corner, then the next layer of the tree is where all places an O player can go, right? I'm not going to go through the whole thing, but you'll see this concept of this tree is something that will appear again and again within AI, and as we make things more complex, we're not going to enumerate the whole tree, but this is the underlying concept. And what you want to do is go all the way down to the bottom, where you'll have a complete board where there's either winning or losing. So, 2 really key concepts in terms of how you do the problem solving, how you enable the problem solving, are knowledge representation and reasoning. And I'm going to talk about each of those in a minute. Knowledge representation is basically different ways of describing and storing what is called the state space. And that tree that I showed you on the previous slide is the state space for tic-tac-toe. Every board configuration is called a state. And we want to be able to consider what's the value of each of those states. And there are lots of different ways to represent states. So it might be a tree like that. It might be a network or a vector. It might be a set of rules, if-then rules, all kinds of things that different ways to represent knowledge in the state space. And then the idea is that you want to use that knowledge and make some decisions about it, what's called reasoning. And so you want to be able to say, well, how can I generate, what are the set of possible actions? And in game playing, if you write any code for game playing, one of the first things you have to do is write what's called a legal move generator. So what are all the possible moves you could make? So if you think back on the tic-tac-toe board, for example, once somebody has put an X or no in a box, you can't then put something else in that same box, right? So that would be an illegal move. So what are the set of legal moves that you can make? And so you need to first generate what are all those possible things you could do, and then you want to evaluate them. You want to say, well, there's 25 things that I can do. Which ones are good and which ones are not good? And then I want to select them, whichever move I'm going to make, whatever action I'm going to take, by referring back to my goals, right? So if my goal is to win the game, no matter what, then I might pick certain things, certain, I want to pick the move which I think is going to cause me to win the game. But I could have another goal. Suppose my goal is to teach my child how to play the game, and I know that if I win every game, they're going to get annoyed and not want to play. So I want to lose some of the time. Right? So there are motivations that, from a human perspective, have common sense, but from a computer perspective, you say to the computer, well, actually, I want you to lose some of the time so that the player is motivated. How do you program that into the intelligent system? There are two general, very broad approaches that are for reasoning. So model-based and model-free, and I'll talk really about those in a couple of minutes. So in terms of the state space, I showed you that tree. How do you use that tree in any of the kinds of AI decision systems is a factor in terms of what kind of method you're using. So one of the methods that could be used, for example, is a vector, or basically a list of numbers. And I've just given you a little example here, which is here. So you have the empty board. And so I've got 9 elements in my vector. Each element refers to one position in the board. And so when the board is empty, all of my positions are 0. When I put an X in a slot, I'm going to change the vector value from 0 to 1. And if I put an O in the box, I'm going to change it to a 2. So you could imagine if you went through with this encoding, taking every state in that tree from the earlier slide and changing it into a vector. Now you have a set of numbers that you could use to feed into one of the processes that I'm going to talk about in a minute. And so this state space, or it's also called the landscape, is a set of all these possible vectors within the whatever the environment is that you're building an AI to play. How do we go from one state to another? This is called a transition. We look at what are the actions that can take us from one state to another. In tic-tac-toe, it's merely putting an X or an O in a particular box. But if you're moving a robot from one position to another, there are a lot of different ways in which those actions can happen. So let's look at how you can do that. So early AI focused on what's called search, and looking at different ways in which you could evaluate the different positions in a state space and determine what's the right thing to do, where am I going to go next. And there are a lot of work on different kinds of search algorithms. But what the important thing to understand here is a couple of points. So one is that the entire search space contains what's called the solution landscape. Might be a partial solution if you haven't finished the game, or might be a complete solution if you have finished the game. And in most cases, even in tic-tac-toe, but certainly in games like chess and Go, the landscape, the solution landscape is so large that you cannot possibly search every single potential move, because there's just not enough time even with the fastest computers. That's called brute force. And you'll often see that there's a some kind of graphic like this that would illustrate the sort of vastness and shape of a solution space. And that's what this graph is meant to show. And the idea is that each point on that graph has some value in the solution space, and we're trying to maximize certain things, and we want to make intelligent choices to decide which way to go. Now, in order to do those things, there are 2 broad approaches that I mentioned: model-based and model-free. Now, most of the world is focused today on deep networks, which is a type of model-free method. But one of the things that's really tricky about these deep learning methods and neural networks in general is that it's very difficult to understand what was the reasoning inherent in the system. Why did a certain set of inputs lead to a particular outcome? Early AI, although there was early work on neural networks and what are called perceptrons. In fact, the first paper First famous paper on perceptrons was from 1945, so even predating the paper by Turing. Model-based methods were the ones that took the most play in the early days. And those are primarily forecasted as what are called expert systems. And the idea was that engineers who were building these systems would go talk to experts in a particular domain. A lot of it was done in diagnosis in the medical domain, for example. And so they went and talked to doctors and say, well, how do you diagnose cancer? What are the symptoms that you looked at? And they enumerated sets of rules, if-then rules. If the patient has a mole that looks funny, then we should do these kinds of tests, right? So these are rule-based systems, and what happened with expert system was there was a lot of interest in typing them early on, but then as the engineers started talking to more and more experts, they started to realize that actually different experts make different decisions. Different experts have different backgrounds, and so the information that they take for granted, which they don't tell the engineer when they're being interviewed, also feeds into the decision. So it gets very hard to enumerate all the possible things that feed into a particular decision. So there's kind of a what's called the AI winter, sort of a slow point with AI, trying to figure out where do we go next. What's happening now is that people are realizing that the model-based systems, which have too much data encoded, too much specific information encoded, versus the model-free, which have basically no what's called model-free, has no specific intelligence encoded in it. We need some kind of compromise between the two, because as we build these systems, people don't trust the output. And so we need to be able to explain how do you get from this input to this output. Okay, and I'm going to whiz through a few more things here. This is just an idea of a perceptron. As I said, it was an early model that was done from the 1940s originally. And the main thing I want to go into the details of this, but there's two main takeaways here. So one is something called the accuracy. So the idea is that you have these inputs, data comes in on one side, and in the middle you have sort of a black box of math that's going on. And then in the outside, you get a prediction, which is often referred to as y hat. So a bunch of data that goes in, you get this predicted outcome. Well, if you are building a model, you actually have the desired outcome as well as the predicted outcome. And the desired outcome is y without the hat. And so we compute the accuracy of the system by comparing the predicted one to the one which we know is our desired one, our correct one, and that becomes what's called the accuracy. So that's one important thing. And then the other thing to take away is that a perceptron is a single layer network. A neural network is a multi-layer network where you just add to the complexity, and a deep network is a network of networks. So just keeps adding to the complexity. And one of the reasons we're able to do that now is because of the advances in computing machinery. And so you may have heard of Moore's Law. We're able to process much more data much more quickly than we were in the 1940s on much smaller devices. And so a lot of these things are now physically possible where they weren't physically possible in the 1940s. The process of learning adjusts the stuff inside the black box to bring y hat closer to y so that our error becomes 0 over time. So there are three broad approaches to machine learning: supervised learning, unsupervised learning, and reinforcement learning. And there are a number of different key elements. We talked about representation in terms of state space. Parameterization is related to representation, but it talks about when we learn, when we adjust the model, what we're doing is we're changing the values of the parameters based on a set of inputs. Okay, so I'll talk about a little bit about iteration. The idea is that you'll start with an initial, like when humans learn, we start by playing a game the first time and you're not very good at it. You play it a second time and get better. And as you play it more times, you get better and better at it. So you are iterating. Okay, computers will iterate many more times than people do because people learn faster than computers do in general. But this notion of iteration is really important. And evaluation. So when you play a game, you learn how to play a game, or you learn how to tie your shoes, or you learn how to pick a strawberry. Every time you do it, you evaluate, well, how well did I do that thing? If I'm tying my shoes and they look okay, well, I'm hurting lace up shoes at the moment, but by learning how to tie my shoes, if you have children, if you taught them how to tie their shoes, it might look great for the first 5 minutes, but then they go to school and like an hour later their shoes can come untied. So there's this delayed reward. So the evaluation, you might think in the middle, and then at the end of the learning, the end of the lesson, that they learned it. But then there's this delay. And the idea with reinforcement learning has to do with being able to get that reward over time. So supervised learning is what's probably most well known. It's also called classification. And the idea is that you have a set of data that you use to build the model. You have a set of whys, so a set of right answers based on a set of inputs. And one of the common examples is a data set that describes flowers, describes irises, and there's a bunch of parameters, a bunch of attributes that describe the different components of the flowers. And the idea is that different characteristics of the flowers will indicate which of the 3 types there are in that data set. And so what we want to be able to do is look at how do those set of attributes give you the right answer. And so that's what's involved in this training, is saying, well, we're going to iterate, we're going to take all those inputs, we're going to say, well, here's what the Y values are, the system will predict a Y hat, and then I compare and decide whether I need to continue learning or whether I want to stop learning and my model is accurate enough. There's 2 phases with this type of supervised learning. There's this training phase where I'm building the model, but then once I build the model, I'm going to take it out and execute it in the real world on data that wasn't in my training set. And so I need to be able to have confidence that this model will give us an accurate answer. We look at evaluating the model. I'm just going to talk really quickly about 2 key elements of that, and that's looking at what happens when you get the wrong answer. When you get the right answer, the output is usually addressed as either true positive or true negative. If I'm looking for a particular type of class, it's true positive if I've identified the correct class. It's a true negative if the example I'm given doesn't belong in the class and I've correctly identified it as not belonging in the class. But when I make a mistake, I have a false positive or negative. And when we want to look at what is the risk associated with getting the wrong answer, okay? It's one of the things that I found it became very, people had an easier time understanding after COVID, because people started understanding about COVID tests and what's the risk of getting a COVID test and saying, well, it has the wrong answer. So with the COVID test, if somebody is well and doesn't have COVID, but they take the test and it comes out positive, then that's called a false positive. And what's the harm in that? Well, it might mean that that person isolates unnecessarily, but there's no public health risk. Whereas the converse is, if somebody is not well and their test comes back negative, then there's a public health risk because they've gone out with this disease. We can look at that concept in other contexts. So look at like fruit picking. With harvesting, if you pick a piece of fruit that is unripe but could be picked, then there might be some negative impact for the grower. If you pick a piece of fruit that, if you miss picking a piece of ripe fruit, then there's different kinds of impact, and different contexts will have different tolerances for true and for numbers of false positives and negatives. So those are things to be looking at. The other 2 methods that are part of sort of machine learning, I mentioned unsupervised learning and reinforcement learning. So talk through very quickly. With unsupervised learning, we don't have labels. We have a bunch of data. We don't know what it's called, but what we want to do is look for relationships between things, between elements in the data. Okay? And so, again, the important thing to notice here is that there's a method of evaluation and there's a method of iteration. We're always looking to improve the evaluation as we train the model over time. Reinforcement learning, something I've hinted at a couple times, looks at, we don't know immediately how well our decision was. We don't know whether our choice of action was right until we get to, say, the end of the game. So the reward is delayed. It's based on looking at trying to build a policy for making a sequence of actions, and that evaluation is done late in the game, when the game is over. So once we've done that and we've built up our AI, what do we do with it? So different kinds of things we can do. We can communicate. So natural language processing and generation are things that have gotten a lot of play recently because of things like ChatGPT, which is a kind of large language model, which basically uses all internet data in order to build models. So all the internet, all the articles in newspapers, etc., on internet are like the input that come into that kind of big black box model and produce some output. Some of the other things, some things that we're looking at in my group is explainable AI. So how do we sort of mix the model-free and model-based methods in order to come up with ways of explaining some of these deep learning models. There are a lot of different ways of taking the inputs and interpreting them, giving some kind of semantic meaning to the inputs. So any kind of sensors, like these are sensors from robots, cameras, and distance or range sensors. How do you convert those digital signals into something that's meaningful? Again, these are ways that machine learning can be used to acquire a semantic understanding of digital data. And then once you've got that understanding, you want to be able to act and use that in certain ways. So whether it's a robot navigating around an environment, whether it's other kind of AI providing recommendations or coordinating things, all different kinds of things that you can do with that knowledge once it's been interpreted. Many challenges within AI, and some of these I've hinted at. Data quality, as I said, only the model's only as good as the data that went into it. Ethical considerations, and we'll talk a bit about that with Craig in a couple of minutes. And different kinds of issues like around trust and other factors with using the AI. So the last thing I'm going to wrap up on to head us towards Craig talk is looking at what AI is good for. And in general, we try to focus on things that, AI is good for tasks that are hard for people to do. So things that involve significant computation, things that have very large search spaces, things that have invisible properties, things that are hard for humans to see, but like a robotic sensor can see. Tasks that are tedious, where people get bored and make mistakes. Tasks that are unhealthy for people to do. So maybe, working in poor working conditions. These are things where maybe it would be healthier if you had a robot, some kind of mechanism doing the tasks. Some common examples of ways that AI is being used, which you may have seen. So on Amazon, you'll get product recommendations. This is using the kinds of clustering techniques, right? Which says, well, you've done a particular thing, so now we're going to look at other people who've done a particular thing. These are commonly things that are brought together. Netflix movie recommendations. So here's something that you've enjoyed or you've watched, maybe somebody else. Other people have watched similar kinds of things. So those AI is underlying those kinds of things. And in the agri-food domain, which I'm going to let Craig talk about in the context of Camden BRI. So I'm going to move on now to Craig, and then we'll come back and talk more specifically about how some of the things I talked about conceptually work in the real agri-food world.
Yeah. Is my microphone okay, everyone? Stop. Yes, okay. I'll just try and stay around here. Okay, I will try not to talk around too much. So good morning, everyone. I don't know about anyone else, but my brain was totally fried by that presentation. So my name is Craig Ledley, and I work for a company called Camden BRI. We're going to have a bit of a change of pace now, because what I'm going to do is tell you a little bit about Camden BRI and the type of work that we do, really to give a bit of context around the food manufacturing industry, which is where I work. So that's the first point I want to make, really. I'm a food technologist, okay? I'm not an AI or data science person. I'm a food technologist. I'm in the business of manufacturing food and drink, or rather, I'm in the business of helping businesses that manufacture food and drink. And I think one of the reasons interactions like this are so valuable is one of the big challenges we have is that the AI community will not have a solid understanding of what some of the challenges are in the food and drink industry, where they might potentially be able to provide a solution. And equally, I've got no clue about 90% of what Elizabeth was talking about. So I'm not going to know what AI might potentially be able to do for me. So it's really important that we have these conversations. So let me tell you a little bit about Camden BRI, who we are, what we do, and the type of work we do. Can I start just with a show of hands? Who's heard of Camden BRI? A few people, but not many, and I consider that a good thing. So hopefully I'll be able to introduce you to the world of food science and technology and food manufacturing. So Camden BRI is a research and technology organisation. What does that mean? Essentially, it means we sit in the interface between industry and academia. So a lot of the work that we are doing is about trying to translate science and technology and make it practical in food manufacturing. We work mostly post-farm gate, so anything from when raw materials arrive in a food factory through to when it goes into somebody's mouth. We're involved in all aspects of science and technology around manufacturing food in that space. We're about 100 years old, so we were established in 1919, originally to set up a new technology called canning in the UK. And canning remains actually a really important part of our business, but we've expanded into lots of different areas of food manufacturing. And I'll talk a little bit about the sort of work we do shortly. The other thing I want to mention at this point is we are a membership-based organisation. So what that means is companies pay an annual subscription to become members, and then they get preferential access to various services as part of that membership package. I'll come on to our facilities and how we use them shortly. So in terms of that membership, we've got a huge industrial membership, something like 3,000 companies in 80 countries around the world. So we're a really global business. Most of our members are food and drink manufacturers. It's essentially any brand you can think about when you pick a product off the shelf. Probably members of Camden BRI. So to give you an illustration of that, 19 of the top 20 biggest food and drink members, food and drink companies globally are in membership. And I think all 10 of the UK food and drink biggest retailers are in membership too. So why do I mention all this? I mention it because it means we've got fantastic connectivity into the food and drink industry, the types of challenges that they have and where they're looking for solutions. So I'm hoping that by having these sorts of conversations, we might find some areas of mutual interest. So in terms of what we do, it's kind of illustrated by this slide on our facilities. So we've got about 3,000 square meters of laboratory facilities. So we use those for routine analytical services for the food industry. So when you buy your food product, and you look on the back and you've got the nutritional declaration, for example, we do all of those sorts of measurements of the nutritional composition of food as an analytical service. But we also measure things like presence of allergens, presence of pesticides, looking for the presence of illegal substances that shouldn't be in there because there's been some sort of food fraud. So a lot of routine analytical services. And then we have a big pilot plant where we can manufacture food products using realistic representative representation of food manufacturing. So that's everything from product development, process development. We might be making bakery products, we might be making soft drinks, we might be making alcoholic drinks, you name it. We work in all sorts of different areas. We do a lot of training, and we've got multiple sites as well. I won't go into that. I'm interested in. I want to move on a little bit to the sorts of research work that we do now, because most people as consumers have got absolutely no clue about how much science and technology goes into manufacturing of food. So we categorise our research into 4 different groupings. We have Canada BRI funded research, clubs, Innovate UK funding, which I guess some of you are familiar with. This is where we have industry academic collaborations, and then pure collaborations with academia. And I'll dig into each of those in a bit more detail. So the Canada BRI funded research and clubs, the CFR research, Canada Food and Drink Research projects, they're funded by our own business. So we spend about £2 million worth of staff time every year working on relatively near market R&D for the food and drink industry. All sorts of different topic areas. I'm not going to go into those now. Clubs are a model where we get multiple companies to pay money into a shared program of work on some sort of pre-competitive area of work. They tend to be quite niche topics, quite sad topics, if I'm honest. So, for example, we've had clubs on bubble structures in bread, where people are interested in how bubbles are formed during the bread proving process and how those bubbles go on to form structure in the final bread. So quite niche topics. We've got one club running at the moment, which is on new technologies to develop to detect foreign bodies, which is actually an area where machine learning comes into play. In terms of the academic collaborations, we've got about, I think, 9 PhD students that we're funding around the UK, including one with Lincoln, with Elizabeth, and that's Amy, who's at the back there, where she's looking at how we can use some AI techniques to help decision-making around hygiene operations and scheduling hygiene operations. So a lot of these are obviously sort of food science technology related, not really AI and machine learning related. I think one area that might be of interest to this group is we've got a knowledge transfer partnership with the University of Portsmouth. So this is where we have an associate working for the university, working full-time with us on a project. And they're actually looking at how they can use data science and AI techniques to help us scrape information, categorise and structure knowledge on a certain topic of interest to us. We're interested in technology trends, basically, and trying to predict what the next big technology might be. So, for example, if you look at something like vertical farming, there's lots of work going on around vertical farming now. 20 years ago, there was probably very little being published on that, but there will have been papers starting to come through 20 years ago. There will have been IP starting to come through. There will be venture capital investment and so on in that technology. So we're trying to spot those little weak signals that are coming through now to detect what the next big technology might be. All right, moving on to some of the Innovate UK work we do. This is really just to illustrate the sort of science and technology we're involved with. So we do a lot of work with the bakery sector, and that's for historical reasons, because we invented a process called the Chorleywood process, which is used to manufacture most bread in the UK now. It uses the Chorleywood bread process. So we've got lots of analytical techniques and our pilot plant, which we use to kind of do research around what makes good bread, what makes good cakes, and so on. And we're using technologies like hyperspectral near infrared, which is on the top right there, which gives us compositional mapping of food products, so we can look at where the fat, protein, and moisture are distributed on a sample. And this is actually technology that is being used with machine learning now to try and do online inspection of products to look for compositional deviations, basically. We're also involved in process development. So this is a project where we developed a new technology to use plasmas, decontamination technology, to basically kill bacteria on the surface of packaging. This is another example of a process development where we were interested in developing a novel method to extend the shelf life of food using ohmic heating or resistance heating. So this new technology was actually first commercialized in 1927, but it's normally done in a continuous flow. And we were trying to use the packaging to deliver the lethal process. So what you do with ohmic heating is you pass an electrical current through the food, and the electrical resistance of the food causes heat to generate the product. You normally do it by pumping the product past electrodes and past the alternate current across it. We were trying to use the packaging as the electrodes and generate heat. I'll skip over that one. So we are starting to dabble a little bit with AI. We are generally not providing the AI technology here. So our role really is providing the science and technology domain expertise. So we've had a couple of projects where we were trying to use AI to optimize processes. One example, we were trying to optimize dough mixing. So when you make bread, you mix up the flour and water and your yeast and so on. You've got to input energy into that dough mixing process. And what you don't want to do is mix for longer than necessary because you're just wasting energy. So we provided a lot of the data for the AI models, and then we used AI to try and optimize that mixing time so that we would minimize the amount of energy we used in the process. A similar project we were involved with, we were trying to use AI to predict when we'd optimally mix ingredients. So we had powders that we were mixing together. And for the same reason, you don't want to mix for too long and use more energy than you need to. You want to stop when that powder is homogeneously mixed. I show this slide when I'm talking about Innovate UK as a funding mechanism. So this is our main funding where we're working with industry. And I show it because a lot of companies think that Innovate UK funding is just for big companies. And actually, this is to illustrate that whilst we are working with big companies like Kraft Heinz, we are also working with a lot of small companies and startup companies that you wouldn't necessarily think can access this funding. So if you are from industry and you're not involved in Innovate UK projects, I really would recommend you look at this stuff. And then just to give you a feel for some of the Innovate UK projects we're working on currently, a real mixture of kind of food science and technology areas. Our main themes are really food and drink safety, improving diet health, sustainability, digital transformation of food and drink supply chain, which I'll talk a little bit more about with Elizabeth in a moment. And they're the main areas that we're trying to focus our research. The process at the end there, I'm interested actually, is anyone aware of what cultivated meat actually is? A couple of shows of hands. It's basically growing meat in a bioreactor. So rather than slaughtering an animal, you can take a biopsy of an animal, put it into a bioreactor and grow living meat cells from that. And then the idea is we can structure that into meat products later on. It's quite a new technology, some way before it's commercialized, let's say, but they're the sorts of areas that we're working on collaboratively. And that's everything I wanted to say in terms of some of the work Camden BRI does. But now I want to have a conversation with Elizabeth about where some of these AI techniques might have applications in food and drink manufacturing and the sorts of challenges the food and drink industry is facing, and whether or not there is potential for AI to provide some solutions. Thank you.
Yep. Okay, good. So I wanted to sort of pick up from some of the things that I was talking about and tie that to some of the things that Craig has talked about. And so I've got sort of 4 questions here, and then we'll open it up for general questions from everybody. Well, the first question I have for Craig, okay, so the first question is what is Industry 4.0? How do you define it, and how is AI employed in Industry 4.0?
I'm pausing because that's quite a good question, really. I mean, Industry 4 was originally coined in Germany, I think about 2010, 2011, and it was intended to be an umbrella term for various advanced manufacturing technologies. So it could be everything from robotics and automation, sensing technologies, all the way through to things like additive manufacturing and 3D printing. AI and machine learning would also be all part of Industry 4.0. The reason I hesitate, though, is I think it's actually become a bit of an unhelpful phrase, in my opinion, because if you ask a room full of people what it was, half of them would look at you blankly, and the other half would all disagree on what it was. But for me, it's getting to the point where we have real-time data acquisition, all aspects of your manufacturing supply chain, right away from your raw ingredients all the way through to the final product. And when you've truly reached that state, you've obviously got vast quantities of data that we can use to start gaining new insights, to start making predictions and forecasting various things and optimizing various things about the process.
Thank you. I'm going to shift a little bit and come back to something I had mentioned towards the end of my talk, which is about the idea that AI is displacing workers. And I did bring up that, we focus on using AI to do tasks that are hard for people, that are unhealthy for people. But there's a lot of play in the press and the media about AI stealing people's jobs. And so we work hard to try to counter that by explaining, why we use AI and the ways in which AI can help the workplace become safer and more healthy and more interesting for people. And we talk about job shift, that you might not need people doing repetitive jobs, but for every piece of AI, for every robot that you put out in the world, you're going to need people to build it, to maintain it, to evolve it. And so there's, I think a shift in the kinds of jobs that people will be doing in order to support AI and robotics as it becomes even more prevalent in workplaces. Is this this concept of worker displacement something that you hear as a concern from the members in Camden PRI?
Honestly, I wouldn't say it's something I hear a lot from the membership as a concern. Personally, I think it's clearly a legitimate concern in that there are a lot of routine, rather mundane operations in food manufacturing that could be automated, that could be done using automation with AI. Having said that, there are also certain tasks that need a lot of flexibility, and humans are probably the ultimate flexible machine, if you like. So I know of companies that actually put robots into factories and then took them all out again because they couldn't cope with the changing demands of the factory. So I think there's always going to be a role for people doing specialist tasks. As you say, Elizabeth, as well, I think we might remove some jobs, some of the more boring, mundane jobs. We'll also create new jobs for people that have to service the AI. I think the other thing I'd add on this as well is ultimately there's kind of a societal ethical dimension here as well, isn't there? We're in control of where we deploy this technology. It's up to us, I guess, to make that kind of ethical choice about maximising productivity versus the societal impact. We've got to make those decisions.
Okay, I'm going to skip to the last question here, which is looking at, sort of following on with this idea. Are there challenges facing the food industry, food and drink industry, where you think AI or robotics could be applied that would help things, and are there areas that people, might find helpful?
Yeah, I mean there are some areas where it'd be interesting to see whether there were solutions that could be met by AI. So I think one of the big challenges in the food industry is always around allergen control, allergen management control. People are always looking for new methods to detect allergens, to monitor allergens. If we could come up with real-time detection and monitoring, that would be a really big deal for the food industry. Most of the product recalls you see in the food sector are due to allergen presence in food products, which shouldn't be there. A lot of that is due to mislabeling or lack of traceability on ingredients, that kind of thing. So these are all areas where I think AI can play a role. We're already starting to see it being used in a lot of routine quality monitoring. So I mentioned hyperspectral imaging. Some people are using hyperspectral imaging to do real-time monitoring of composition. People are introducing machine learning to detect defects in products on product lines. And that is the sort of stuff that sometimes you see manual workers doing 100% inspection, and there's no reason a machine couldn't do that better and give that person a more interesting job.
Great, thank you, Craig. I'm going to open up now to questions from you, and I will also just put up the last slide. So feel free to reach out, whether you're in the room with us or you're watching online, feel free to reach out to myself or to Craig if you have follow-up questions. So questions in the room? Yeah.
How can AI go about making decisions about setting its own goal states?
So usually AI is built by engineers with some particular job in mind. So you could devise an AI that says figure out what your own goals are, but it might not follow with what people want it to do. Yeah, it's kind of a vague answer, but it's yeah. You could tell it to learn its goals, but coming back to some of the thought that I was showing you, the development of the learning process is all predicated on being able to evaluate the solution and say whether something's better or worse. And if you're telling an AI to just come up with something, it will have no way of knowing whether it's better or worse without having some litmus test against which to evaluate it. So there's some early work that was done actually in the graphics community in the 1990s by a guy called Carl Sims. And you sort of Google this really neat video. What he did was trying to evolve simulated creatures to learn how to walk or learn how to swim. And so he gave them some goals, very simple goals like, walk from here to here. And then created these different structures that gave it, components that you could have if you did build as a physical structure, and then ways in which those components, physical components like rods and plates, how they move and interact with each other. But then just gave it to this AI with an evolutionary learning system to just learn how to walk. And some really interesting stuff to see. So it's a way of giving a very vague goal and very vague building blocks that did demonstrate that you could achieve something over time.
It kind of comes out as an emergent property, right? Intelligence isn't necessarily something that is predefined. It's an emergent property of a system. So how can you design a system to have an emergent property of intelligence and decide what is the concept?
So within AI, we talk about emergent as something that comes out as some result or byproduct of what the goal was that we aimed to have. And so, some of it, the notion of emergence is really in the eye of the beholder, whether this was something that I designed the system to do or something that was a property that appeared once you build the system.
Any questions, Craig?
Yeah.
What are the regulatory requirements for the detections system?
I missed the last part of your question, sorry. I had regulatory requirements and then this.
Regulatory requirements for example, allergens detection system that you mentioned later.
First thing I'll say is
Particularly for AI systems.
I'm not a regulatory expert, so I can't give you a sort of fully comprehensive answer to that question. But generally speaking, in the food industry, we have this concept of due diligence, which is where you've essentially done everything that you could reasonably be expected to do to prevent an incident. So in terms of allergens, there are specific requirements around the amounts that need to be, in terms of the detection thresholds, rather, that need to be met. But I'm not the best person to talk about that. But if that's an area of interest, we'll have a follow-up conversation.
It's a great question because the answer is there isn't an answer because they haven't really gone through yet. But regulation is going to be the next thing. So it's sort of question for really a whole lot. And the particular one is going to do false positives, false negatives, all those real consequences. One last question, we have to wrap up.
Gary Wilkinson, Decision Lab. I'm interested that Camden and BRI would be an interesting talk because it seems to be more involved with the production and manufacture. Here at the university, the robotics, 3D graphics, the strawberries and such like.
Yeah.
So these are kind of two ends of the food chain.
Mhm.
And with the organizations involved, they're all very commercial, like clients and so on. The information sharing that's needed seems apparent for these AI systems to learn and develop this processes and optimization. Is there any initiative around data sharing? And, how open are the companies and organizations to allowing the information that they get from their production lines and activities on farms as well?
There are initiatives around data sharing. It is a thorny issue, and obviously some companies are more receptive than others to sharing data, and there's always the sort of discussions around who owns the data and all that kind of stuff. So yeah, it definitely does need to be bottomed out, because as Elizabeth said, until we've got that connectivity and we've got clean, transferable data that can be used right across the system, we won't realise the true benefits of AI.
It's, I figure it's a bit like dark comes to sense. AI will not happen unless we can get the data sharing. And that's one of the big issues that we think about 20 years. Rather regular. We can figure out these enabling.
But there have been blockchain platforms developed, for example, there have been case studies where people have demonstrated complete traceability through the supply chain from the raw material through to the consumer with blockchain.
Just wondering if there's any initiatives to do.
There are, it's number of.
So just one thing to point out is that when we build the models, we can keep data separated. So if a company says, well, I've got this process and another company has a similar process, we can use all the data from one company in isolation and build the model. And then we can adjust the model on the data from the second company, again, in isolation, and protect the privacy and the sensitivity of data from one entity to another.
That really is about those data exchange data that environment is the big issue. Right, with that, I think we're there. Thank you so much, Elizabeth and Craig. Anyone wants to get into detail with these guys, please do. They're absolute world leaders in what they do. What we're trying to do here is bring together the AI, the deep AI, with the practical applications, which I think they both do so well. So thank you very, very much indeed. Thank you, audience. Thank you for coming. Breakfast briefing. Next one is at Springfields in Spalding. We're changing the location. It's going to be around the cool chain. Members of the team of National Food Manufacturing have done a big review with the LEP on cold storage and infrastructure for the food industry sector. That will be the discussion point. Please come to that. Enjoy the rest of your day, and thank you for coming.